time with our regular Thursday secret seminar. And as regular chair, it's my great pleasure this week to introduce Jeff Kimble. Jeff is the William Valentine Professor of Physics and Professor of Physics at Caltech. He is a pioneer in trapping and controlling atoms. He's known for the first convincing demonstration of teleportation, and these days he's interested in quantum networks and hearing about the integration of cold atoms in nanophotonics. He also wanted me to let you know that he's as tall as he ever was. Most people reach their peak and start shrinking, but he's stayed at that same level. Very happy to have you.
That was incompetent.
Okay, well, I want to give a fairly broad, it's in a particular area, but some theoretical stuff. And then if the things we're trying to do, if only you could succeed, would be important. Because they're really hard stuff we're trying to do. And there's no point to do it unless it's worth the effort. And so that's the broad vision, and then there's some nitty-gritty details that I'm going to have to tell you about, which you can just kind of sit back and look. When I was a graduate student and I had to do Morse-Feshbach and I got the Green's function part of it, it was kind of a new profession. But that's what I'm doing. Underlying simple stories of the world. So there's had to be developed, not by me, but by a broad theoretical community, new ways to understand how atoms and photons interact. And then I would say rather modest progress was made in the laboratory to actually implement the cartoon pictures I'll show you of 1 and 2 dimensional lattices of atoms inside dynamic structures. But how that, what we're doing in the lab really is foundational to, we have to know all this stuff about Green's function. So, let me begin by just reminding you about, this is all quantum optics, atoms and photons, and over the decades there have been traditional ways to achieve interesting phenomena associated with the way light and matter interact. We'd like to have this blue thing as one atom, and we'd like to have that one atom interact strongly with the photon. So just this little picture of lens, just get your photon somewhere, focus it to an area lambda squared. That's roughly the radiative cross-section of an atom. And so there'll be strong attenuation of the one photon going through. It could even reflect, part of it transmit. You could entangle the photon with the atomic state, part of it going one way or the other. If only you could do this. Well, the story turns out to be a lot more complicated than that. And nobody's done a very good job, I would say, of strongly coupled propagating light onto an atom. And we can talk about why. So if that doesn't work so well, get a cavity and just let the light bounce back and forth over and over again. And if you have a cavity, as many groups in the world, including mine over the years, with finesse where you have kind of a million bounces, then the interaction with the atom can be much stronger than I think in any other setting. If you don't want to deal with one atom, then get a lot of atoms. And the equivalent of how strongly the photon interacts as it comes into the cavity bouncing around is how strongly does the photon interact rattling around with the atom. So the optical depth of the signal. Large optical depth is good. And then for photon-photon interactions, this little cloud, this is an atom, and then excite the atom to a Rydberg state. And Rydberg interactions when the atom's in the excited state very long interaction, very strong interaction with neighboring atoms. And so one excited Rydberg atom can change the energy level of atoms in the cloud of, say, 5 microns around it, and choose them to interact with the photons differently. And that's been kind of the set of most powerful techniques that have been developed. And they're really good. I've spent a lot of my life trying to do a lot of that. But I think there's a better way forward. It's certainly new. And it's to try to do all of this in one setting. And the setting is atoms, ultra-cold atoms, and nanophotons. And the reason to do this is they're just remarkable properties of modern lithography and dielectrics, things that you can pattern in a fabrication facility, where the optical losses can be well above 10 to the 7, the quality factors. And the efficiency of getting photons in and out of where you're going to have them interact with atoms can be very, very strong. Efficient. Kerry Vahala in some of his work has demonstrated 99.7% mode matching, if you want to call it that. So cavities all in a big array, it looks good on paper, but you can't get the light in with high efficiency. And so there are all kinds of non-photonic structures, parallel beams like this, space like these are dielectrics and vacuum. We've got to have some vacuum space because I want to put atoms in. I don't want to deal with solid state atoms. Here's one I'll tell you quite a bit about. This light gray is a dielectric, silicon nitride, and the background is just vacuum. This is a structure suspended in vacuum. I'll tell you quite a bit about that. This is another system we made at Caltech I'll tell you about. This is a waveguide. It's a defect waveguide. This looks like it wants to be some two-dimensional structure, but we put a defect in there. I'll tell you about that. And if you look at these pictures, it's like, wow, here's another one. This is a honeycomb. This is the gray, the silicon nitride. The black is vacuum. And these look like I made them in PowerPoint. These are actually SEM images. We can make these at a level where we can, having made it, you can't really with conventional SEM see the errors. That's over 2 nanometers scale. Now what we want to do, these are incredible structures, very low loss. We want to give them quantum functionality because they're just linear dielectrics. So what we want to do, that's the mission today, is to put atoms in like that. And it's really easy in PowerPoint, and towards the end I'll tell you how hard it is in the real world. But now these are functionalized dielectrics that become quantum dielectrics when you push into the atom. And as I'll describe to you, you can do amazing things in terms of both photons and phonons, these structures of mechanical modes, and you can have atom-atom interactions mediated by single photons. Really strong interactions that you couldn't get without these dielectrics. And for a physicist, you might feel ashamed to say, I did at the beginning, we can engineer the character of the interactions. Oh, I don't want to do engineering, that's why I'm a physicist. No, you can engineer the fundamental radiating properties of atoms. So that's the kind of why. Here's this slide is all the understanding is based on this. So if there's a question, slow me down. I'm going to take a small, say, piece of silicon dioxide, just glass, make it 400 nanometers in diameter, and make it really good, smooth wise, and then just propagate an electric field along. Some of the field will be evanescent, and it goes through, silicon dioxide is optical fiber, and you go tens of kilometers with very small attenuation. So this is really good. This is going to be a piece that's only maybe 100 microns. It's going to be very low loss. And now put an atom in the evanescent field. The field of this spreads out a little bit into an evanescent tail. And when the light comes by, the atom can be excited. When the atom's excited, it will emit light in the free space. That rate's going to be called gamma prime for the whole story today. And it can emit also, when it goes back to the ground state, the atom into the waveguide. But this must be a completely fiddly effect. There's one atom on a macroscopic level, 400 nanometers, but there's a lot of atoms. So what's one atom going to do? Well, what it can do is reflect the incoming light a little bit. Because this is like an impedance mismatch. The guided mode that you saw from Helmholtz equation is running along, and now this is not what was in Helmholtz equation. It's so low. So part of the light will be reflected, part will be reflected. And the amount that gets reflected is just the ratio of this into this rate into the waveguide divided by the total rate. So there's only one ratio. Factor out gamma 1D. The size of this emission in the free space relative to gamma 1D, the emission of waveguide is the whole story in the simple dimension. So how big is gamma 1D? In terms of the Einstein egg coefficient, and gamma prime in this setting is very open, so that's a gamma prime of 0. That was gamma 1D, the emission into a waveguide, is set by two things. is set by how big is the node area here. The radiated cross-section of an atom, it's an area, it's just lambda squared over 2 pi. That's ejection. 3 over 2 pi lambda squared. It's the resonant cross-section of an atom. So I've got to get the light focused better than that to get a big interaction. You think of it as just scattered cross-section of an atom. So that ratio, make the effective area small. That's why nanophotonics is useful, because you can design the light in a very small cross-sectional area. The other thing is that the light is going slower in this dielectric than it would in free space, so I need to know the group velocity. And roughly, if you just had the fiber, the group velocity is just, for a piece of glass, 1.45 is the phase of group velocity. So you don't win a lot. The group velocity is 1.45. It's smaller than the speed of light, so this is a factor of 1.45. But I'll show you in a minute that this group velocity can actually go to 0 in certain structures. So this can be really big. So those two factors of this ratio of this to this. And this is the simple story. What does this area really mean? Well, you don't want to know. It's just, you know, how big is the node? That's where the electric field is concentrated. So just to give 2 examples, if I did a nanofiber, and this has been pioneered by a group in first in Germany and then in Vienna on a Wassermühle school, to really demonstrate trapping of atoms along structure like this. Then you can have the transmitted light compared to the input light, you can have 5% absorption. So 95% goes through, 5% absorption. That means the amount reflected is very small. It's a few percent. But nonetheless, you can see the bump in impedance of the atom. On the other hand, if we use what's called a photonic crystal, which I'll talk about in a moment, think about these 2 parallel beams of dielectric. This dimension is 100 nanometers, this is a couple hundred nanometers. Then there's a big open space, so the electromagnetic modes can fill up this space where the atoms can be. We don't have to do anything with this tail. But as I'll show you in just a moment, this structure lets the group velocity get very, very small. So I'll get a big enhancement from that. And in a structure like that I'll show you, we calculated, we've done some measurements I'll show you later, that this transmission coefficient, which is 95% here, can be 1%. That means that a single atom inside a structure like this can attenuate the light 100-fold, just in terms of a single photon. So that's good. That's a lot bigger than ever will happen here, and that's the kind of thing we want to talk about. Now, not unstructured waveguides, but photonic crystals. So this is the beast we've been dealing with. Both ends of this are dangerous. And this is the thing I already showed you. So it has this modulation. You may ask why. Well, we have to have a waveguide, and we need a vacuum space. But to get a photonic crystal, we need to modulate the index refraction. So then we get a crystalline structure just walks through. And so modulating on the outside of the we have defects that are farther away from the atom. What we want to do is put an atom inside, right in the middle of this thing, which is 250 nanometers in this particular structure. And I'll show you how to calculate it. In that case, we should have this ratio. This is the critical ratio. The amount into the waveguide is much bigger than into all the other modes. We should have 90% reflection, 1% reflection, 100-fold attenuation, 60. And in terms of things that if you've been in quantum optics kind of your whole life, you know that 1 photon can make an atom mutate at a rate of 10 gigahertz, which is about 50 times bigger than ever was achieved before in the optical domain in which Ernst and I did, and in the conditional feather probe. And how many photons do you have to put in here to saturate the atom at 10⁻⁷? So 1 photon is really a big deal in this thing. The other thing that a quantum optics person wouldn't know, I didn't know, there are these things that result from this. This is a dispersion relation, a band diagram. So on this axis is the wave vector, the so-called projected wave vector for light propagating here. And on this axis is the frequency wave. So this is one band, this is the other band. They're folded over. All the information is in here. There's blocks there outside of the distance that are very hands-on. It's minus over here. And now there are interesting things to do. The first is if you go to the band edge, you notice that this guy goes flat. This is omega, this is k. d omega dk is the group velocity, and just at the band edge, the group velocity goes to zero. So the group index goes to infinity, and that's the enhancement photon. That's called the Van Hoff singularity. So you get that. The other thing you get is this wave vector engineering. In free space, if you have two frequencies, they absolutely have different mean squares. So if you're trying to do atomic physics, we trap atoms with one frequency of a trap, and then have interaction with light with another frequency, the least goes with mismatch. And in a structure like this, you can have one frequency that's a trapping frequency, say for cesium, this would be the D2 line, and the other, which is an interaction frequency, which is the D1 line, and they can have exactly the same mean square. And if you don't like that, you want them to be 1 over E or whatever, well, you can engineer that. So that's good. That's all one atom, single atom physics. What if we put a lot of atoms in? Well, that's what I want to talk to you about. I didn't embark on this adventure 6 years ago just so we could have a better one atom physics. What about a lot of atoms? One atom gets excited, emits, talks to the other atom, that one absorbs, re-emits. This thing is automatically wired up for quantum numerical physics. If I could get one atom trapped with 3 or 5, I don't have to paste together different modules to access the quantum numerical. So that's a big advantage to trying to learn how to do this. To make these as perfectly as we can and really densely fill lattices. There are lattices of the dielectric of the photonic crystal, and there are lattices of the. So that's the goal. In that setting, this is a band structure, toric band structure. This is projected K, this is omega. And now in this alligator, let's imagine we built it, and now we designed all the geometry so that the atomic frequency is there. At that place, if you have an omega of the atom, the transition frequency, the K, so they're propagating modes, they're going left and right. And they're just even 9K. They've got a complicated shape and polarization in general, but they're just propagating up and down. So if we put an atom in there in excited state and it emits, the photon can propagate over to another atom, be absorbed, and propagate back. So these two atoms can exchange excitation. If one's excited, goes to ground state, excites the other. That's a spin flip in this language. So the spin flip, this one emits, this one absorbs, this one is completely conservative. It has a rate, which is just the Scannell that we talked about. And there's some functional dependence about how far away the atoms are. So for example, if you're at the edge of the Brillouin zone, close to here, then this thing is not propagating mode, it's a block mode. It just has cosine squared. There's another term, this atom emits a photon, and the photon can just leave by itself, or it could induce this atom to emit, and they're both photons. So there's two atoms have different dissipation, emission into the wave packets than single atoms, and that's described by something called the Lindblad operator for this collective dissipation. So imagine we chose to trap the atoms, a bunch of them like that, and then what happens? If we put some photons, these are all ground state atoms, so to get a spin flip, we've got to provide energy. We've got an excited atom, and then it can decay, go somewhere else, and excite another atom. And what kind of processes happen? Well, there's this happening, this coherent evolution of two atoms exchanging, and then this dissipative stuff. And the figure of merit, that is to say, whether I'm interested in this one or that one, is just this ratio. You might say, well, why would you ever you want to get rid of that? Well, I'll tell you how to do that in a minute, because it's a dissipation, it's Lindblad operator. And just to emphasize that that's not true in this study, let's place the atoms as they're shown. The unit cell in this is from here to here, 370 nanometers. This term, this functional term, is zero in that case. And so now what can we do with just collective dissipation? And to show you that there's interesting things, that this is worth the effort of a grown-up to be working on. Here's a paper led by Ana Garcia, and their change group. And the idea is to put some atoms in an nanofinite time order, 1 × 10⁶, 10 or 20 or however many you get. And then let's use that as quantum memory. So we're going to send a photon in, map photon into these atoms. Remember the pictures I had a really powerful way to store quantum information in atomic ensembles. This is a baby ensemble, so we're going to map photons in and out of it. So if I had an excitation stored, I can map it out and then back in. If I have a single photon, put it on the beam splitter, I can send half the photon over here and half the photon over there, store them for a little while and map them out. Map just this one out. So that's a quantum memory. And the question is, how big is the error in that storage and retrieval? And in all of quantum optics, whether it's in cavity QED or atomic ensembles or anything else, there's a scaling of that error. Or 1 minus the fidelity is an error, an infidelity. And what Anna was able to show is the infidelity, which is the error, versus the atom number scales exponentially. This is the best known in a number of settings. Scalings in other settings are 1 over n. If you have n atoms, the best known scaling is 1 over n. More typically, it's 1 over the square root of n. Cavity QED with 1 atom is 1 over the square root of quadrant n. The square root of n is essentially the optical depth for atomic ensemble. And this is exponential improvement. So if this ratio I told you is a critical ratio for this whole story, gamma 1 given gamma prime due to its group, and you have 10, 50, 100 atoms, then the errors you make are exponentially small. And that already is a slap in the face that says, wake up. I don't know anywhere in optical physics where that's true. The only place I know where that's true is in superconducting. Exponential suppression of errors for protocols like that. I will say that I won't go into detail about this. This is not the first point. This is either. In a way which I won't describe, I've been talking about a photonic crystal, maybe the dielectric. But get rid of the dielectric. Look at these atoms. They're just little bitty dielectrics ordered. So there ought to be band structure for the atoms too. And this miracle of exponential improvement rests on this pioneering work of Ivan a long time ago about how arrays of atoms have band gap, have a band structure. And it's the interplay of that band structure of the atoms with the band structure of the photonic crystal, which is fundamental to this. Okay, what else can you do in these little dielectrics you can't do in free space? There's a whole new field of what's called chiral quantum optics. There's a review article by Peter Lovell, one of the pioneers with quantum dots, and Arnold Rushmule, pioneer with atoms, and others in this review. And so let me give you the kind of simple story, surprising story of what can happen in dielectrics. This is a dielectric. It's not a very good picture. It's here. It extends to plus and minus infinity. This region is dielectric. This region is air. So this region is air. So it's just like the alligator, but I threw them 1/2 away. So it loses its bilateral symmetry. And now what I've shown you is if as a guided mode propagates along like this, these are modes that solution to Helmholtz equations. They're guided, they have no loss in the ideal phase. The polarization rotates around. So it's circularly polarized light going this way. Up here, the right-hand circular polarized light's like this, and down here, it's has the sense like that. And to show that better here, there's sigma plus and sigma minus, the color coding, and sigma plus and sigma minus down here. And how circular can you make this? Right here, this is the ratio of one-handed relatively to the other is almost 100%. So if you put an atom in there, the atom will interact with sigma plus. The atom's not going to interact with sigma minus because there is no sigma minus there, and the atom doesn't do that. So if you have a simple atom like this, and like this, trapped in these holes, and when the light propagates this way, it can only excite that transition. And when the atom's excited in that transition, it can only decay that way, it can only decay that way. So this is called chiral, and this is an atomic emission can only be in one direction. It's a linear dielectric, so it involves time reverse invariant. So if you propagate the backwards way, this picture's just reversed. The blue's up here and the red's down there, and in that case, an atom trapped here would interact here. If the light's coming that way, it would interact on the receiving lines. And the thing that's kind of surprising, if you haven't seen this before, when light propagates in free space and it's circularly polarized, it's polarized in the plane perpendicular to the propagation direction. This is light which is polarized as it propagates, it's circulating like this. That's really strange. And but it's inherent in the little dielectric. If you focus light to the scale of order lambda, you instantly get components that are both the same size. Longitude and temporal. In the structures I've shown you, the alligator, we worked hard so that it's predominantly just one polarization. We've gotten rid of that other stuff, got a nice single polarization for the atoms to interact with. So that seems kind of innocuous, but with this chiral quantum optics, you can do amazing things. And the most amazing thing that's been done so far has been done by Hans Pichler together with Peter and Mikel. And what they show in something I won't go through, but I encourage you to look at this reference, is that you chiral dielectrics like this, you need to have gamma 1b over gamma prime big, so that this emission into the waveguide dominates free space. That you can actually make amazing states, cluster states, 2D cluster states, and, other kinds of exotic quantum states, and a very simple state. One atom trapped like that is okay, let's look at another regime. Here's a photonic crystal, just for cartoon purposes. Inside the band gap, let's build the structure. It's cesium, I tell you that at the beginning, so let's build the structure so that the atomic frequency ends up inside the band gap. That seems kind of dumb to do because fields don't propagate inside the band gap. And so, what happens to the atom? Well, if you put an excited atom in a dielectric like this, it will try to emit into the waveguide, but there's no propagating mode. So what's made is a kind of photon cloud of atom excited and a cloud of photon around it that was first described by John and Persson in 1990. And since then, in a number of other studies. And so how do we do interesting mini-bite physics in that? Well, just put another atom over here. In the setting of this one-dimensional structure, these really are exponential. So the scale looks highly between banded. In this case, now we have the same kind of Hamiltonian. There's some kind of U that tells the spatial structure of this envelope. There's this collective dissipation that we had before, but now this is inside a band gap. And in an infinite structure, this is strictly zero. In a finite structure, the dissipation is exponentially suppressed. It's just how long is that, what is the size of that tail when you hit the end of the structure? So you can exponentially suppress the dissipation. What if you put a bunch of atoms in there, then you get a bunch of these overlapping tails, and the ability to do this reversible evolution is just set by how big is this trying to compare to the residual structure distribution, which I'll tell you about how we can engineer that. It's not just an extended coefficient. So that's the Hamiltonian. This is the size of the interaction. It's something just C-number function. But it's something other than just this. If you take roughly the gradient of this, then you get forces. So an atom that's spin like this and like that have this J that tries to pull them apart, or push them together. And the size of that force is just given by the gradient of that in the classical stream. And you can change the structure of this just by where you can relatively random. And so this gives rise to interesting Hamiltonians that are different than, say, a lot of work in spin Hamiltonians in matter, because in that the center mass degree is a quantum variable. And the motion, the external motion, is inherently tied to the atomic degree of freedom. And the kind of leading working evidence for the chain to show how you can generate theoretically generate new exotic quantum phases for spinning motion separation. The other thing you can do is that J is a spin-spin interaction, so it's actually, here's the energy level of the atom, and if this atom's excited, it can make that atom, it can change the energy space. So what's the dielectric constant of this atom? It's something that looks like it's epsilon as a function of frequency. And it depends on where that shape is, depends on the frequency. If this atom gets excited, it does a dipole interaction with that guy and changes the structure. If there are photons propagating and the atoms now are dielectrics, right, this atom being excited non-locally changes the dielectric constant over here. So two photons can interact through the atomic medium, just like two atoms can interact through the photon. And this is a calculation by Derek, Douglas, and Shimon. And what you see is a pair of photons injected and propagating, and this is how they would propagate along a straight line, but now you see that they oscillate. So you can arrange this interaction so that the spatial structure of the dielectric constant, which depends on where the first excitation is. If you have a bump in the dielectric constant, that makes photons attract each other, and a valley will help. So you can make two photons bound, and you can make molecules, propagating molecules. They've done two. The question is, how do you extend this? 1, 2, 3, 4, 5. Can you make a long linear chain? And the question is, can you make finally quantum dielectrics? In this whole story, I showed you the band structure, and it's this big piece of dielectric. In that structure, 1, 2, 3 photons in the medium change the band structure. They renormalize the band edge. So a chain of atoms like this can change the band structure from you go straight through the photon to perfectly conditioned on 1, 2, 3 photons. You can do all of this in 2D. I won't go through that. This is work done with the Ignacio Chirac's group, led by Alejandro Gonzalez-Tudor, and so you can get more complicated band structure. This is this projected band diagram, direction you're going in the crystal, and frequency. And what we needed was flat parts, that's like the omega decay, to enhance the interaction. And we need other flat parts. This is to make a trap, and these other flat parts to enhance the interaction. So the two band edges of the algorithm I showed you before. And we've done a lot of work to show that you can do quantum mini-body physics between the atoms and structures like that. Atom-atom interactions that are photon-mediated, photon interactions that are mediated by the lattice of the atoms, and these quantum dielectric. The question is, nobody knows. In a 2D structure, can you make 2D molecules of photons propagate along and somehow respect the lattice symmetry as they propagate? We've also looked at trying to make arbitrary spin-spin Hamiltonians. You know, in the story I told you, you see this exponential. In 1D and 2D, it's some kind of Bessel function, and that senses the character of the interaction between spin I and spin J. Could we make that an arbitrary interaction? And so this is just a proof of principle in this paper to show how a famous spin Hamiltonian is better. There's something called a Hellman-Shastry spin chain. It's got a really wicked, evil kind of coefficient. Can we achieve that? Can we achieve that in this 1D structure? Well, no. This is a periodic structure. Yes, you can. We can connect every term in this, including that this end connects to that end. So we can arrange the boundary conditions. That's shown there. In 1D, we've also looked at 2D things. We did another famous spin model by Haldane. The topological flat bands, this checkerboard, time reversal, violating interactions, and it's all worked out in some detail in this paper. So, short stories, it seems like it's worth the effort in terms of this kind of these tour model. So now I want to go into well, this is the space between the toy models and the laboratory. We have to fill up to understand the reliability of all the models, and to understand if we build structures, what kind of characteristics we have. And the beginning of that for my group was with Oscar Painter beginning in 2012. But for me, the origins of this in quantum optics date back to Gary Shackelwell's work. As far as I know, quantum optics really first expressed all these interaction terms of this atom interacting with that atom. Is it this dissipative interaction, or is this conservative spin in terms of Green's function? More modern work on that as well. And so there's the foundations of all this physics I've been telling you about. What's the theoretical way we're supposed to calculate it? And given that theoretical way, how the heck do we really do it? And I'll touch on both of them. So here's a photonic crystal, just chunks of dielectric, so a lattice constant like that. And now what I want to ask is, the atom near these dielectrics, it can be symmetrically placed the way I did it, or I can put it in a corner or move it around. If I'm going to trap an atom, I have to know what kind of polar is. That's van der Waals forces near a dielectric. And so how do we calculate that? This has some permeability, permittivity. How do we calculate that? Well, there's this historic work, but this is the work that we've used that says, how do you do it in a way which we can actually numerically implement? All of this is numeric. And that was only known by applied mathematicians. How you do this numerically. And so, how big is the Casimir folder? Well, next to a wall, you know it goes to really close, like one of those CTs, the distance to the wall. How do we do that generally? There's some kind of Green's function. There's some kind of atomic polarizability. And then you've got to do this interval. Well, in a wall, you actually know the mode functions. You can do the same thing. In a geometry like this, forget it. This is a pretty big frequency range. And so all the numerics that people had tried up until this work of the MIT group were just not successful. Not applicable to the type of thing I want to do. The thing we're trying to solve is actually pretty simple. This is called the scattering Green's function. And we just need to know the solution of this Maxwell equation. There's a point dipole, and we need to know that Green's function. So this is classical linear physics, but it was pretty hard to learn how to solve that. We didn't learn. The way to do that are modern computational techniques kind of do that. And so if you know that, then you can calculate Casimir folder. So this is an example. This is a little piece of dielectric. These are kind of 200 nanometers. This is a few hundred nanometers, and it's got holes. So it's a photonic crystal extends to infinity in all directions. And what we want to do is trap atoms inside it. So the trap we would use is light at the guided punch. We would make essentially an optical tweezer out of the guided punch light and trap the atoms in there. This is what the trap looks like in various dimensions. It's maybe easier to see if I put the cuts on. So we're going to trap atoms, different cuts. Along this axis, that's the guided mode. If you go near the Brion, into the Brion zone, the lock function is just cosine squared. So that's very robust. The red is Casimir folder in the middle, along the axis, and the blue is the total trap. The dash is the part that's the optical fort of the guided mode. What if you go in the Y direction? Well, that's this direction, and the walls are right there. Casimir folder is just gunning for the atom. It's going to suck it into the wall. And so this is what you would calculate if you only had the optical potential. The Casimir folder looks like this. This is something that you don't know how to calculate until you go that Green's function. So you add those two together, and you barely trap. So Casimir folder is really dangerous for atoms. That's the dimensional instant. And now look at this trap. This is in the Z direction. This trap, the light provides no confinement. There's actually a nodal line of the optical field. So there's no confinement. and yet the atom's trapped. And that's because Casimir-Polder, which is the red back, the total use is the total. The trap is completely made out of nothing, made out of vacuum forces. And you wouldn't necessarily know how to do that, but Qinglong Hung in my group now at Purdue figured out how to do that. This is a trap which in this dimension is completely, the atom will be completely confined by water. So that's in 1D. We're trying to do that. We haven't succeeded. Here's in 2D. This is subwavelength vacuum analysis. Imagine now that we're not doing optics, the size of everything I showed you before is set by essentially lambda over n, free space wavelength over the dielectric function, or the image refraction. You can't go down to these small distances fitting in light of an optical wave that just has no contact. You can't make traps where the light's bright. But Casimir-Polder, the interval 0 to infinity, there's just not enough screen. So if you look at a thing like this, Casimir-Polder can be big here, it's right above the dielectric, and small here can be not much dielectric, and big here. So if you go like this, you get a modulation in Casimir-Polder, like this. Along this direction. If you go along this direction, you end up with you go along that direction. It's a 3D like an egg particle. Completely confined. The atom, if it tries to go away, is away from the surface, is confined. And so it's completely confined in 3D on length scales. Trap sizes of these posts are like 25 nanometers. But what I told you can't be right. Because everybody knows about this no-go theorem that says if you use linear dielectrics, it's impossible to achieve 3D trapping with vacuum forces. So what's the catch? The catch is we achieve in this diagram 2.5 degrees of freedom. The atom is trapped in X, Y, and in Z going away. But of course, the atom wants to crash here. The kamikaze atom wants to crash on here. And so we have to send a laser up that provides a repulsion from the surface. That's not too hard because these things are so small. If you send a laser through there, it's essentially like a particle. It really doesn't care about the color. So then you can make a repulsion. So that's stuff you wouldn't actually think of at first sight. We're going to do atoms and small dielectrics, and that's only bad news because it doesn't hold it on the The other thing we need to know is that's Casimir-Polder. Well, I put an atom there, and what's this gamma 1 do? Well, you calculate that by some other Green's function, and there's some technique. There's different ways to do it. Our favorite way is what we're doing, and a lot of mathematicians. And so then you have to do it. This is again the atomic polarizability. And so how do we find out how an atom is going to radiate? You need the 1-point Green's function of the atom radiates, and what's the strength of the radiation back at the atom. That Green's function has 2 components. One's real, one's imaginary, and that one is the imaginary component. And if you do that, this is Qinglong Hung did, as a function of frequency, what does this look like? Well, the thing you instantly see is this region. And this is the cesium B2 line, but the structure has been built to have a bandage. So all of these things are bandages. This bandage for the TE node, bandage for the TM node. And if you zoom in on this, this is this gamma total being enhanced as you approach the atom. And what you see is that for different polarizations and different atomic states, this enhancement is vastly different. The dashed line is for a shorter structure or a longer structure. As you go longer and longer and longer to infinity, this thing actually goes. And so this gamma 1D over gamma prime, in this calculation, if you polarize the atom correctly in between them, that means that the attenuation in this structure would be 300-fold. Okay. That's the total emission rate. How do we find out to differentiate gamma prime and gamma? Well, in a normal world, the way you can find that out, if you go look in Morse Pressback, is that the Green's function can be expanded in the ID modes of the structure. We don't know the eigenvalues of this structure. This is all numerics. This is an open system. We don't know those, so there has to be some numerical technique to figure out that, which I'll show you in just a minute. Okay, so you survived the interlude. That's the nitty gritty that's behind all these papers that we did publish in both here. So this is our hero. This is this alligator waveguide here. It's connected to the world. Light comes through an optical fiber, comes into this little waveguide, very efficiently propagates, and finally gets to this region, comes in through the fiber. These things are tethers that hold it taut. This is fully suspended. Again, this is the dielectric, and the darker gray is nothing. It's back. And so it's taut under about 700 megapascals of stress, so that it stays warm. And then this is what it looks like when you put it on the holder, and the fibers come in and out to get light from the outside world into the device. And this is what it actually looks like. See how good. So there's this impedance matching, and then there comes the little It's a bunch of SEM images stitched together. And it comes out. I just thought it's 700 megapascals, so the first 6 months you try to build these, everything you build just snaps. You're not controlling the fabrication. And finally, you don't know what to do. Just the heroes of this are something who made our first effort. And so then you try to trap atoms. This is the band diagram. So this is omega, this is K. This is what it looks like on the edge. And this is take an SEM like this. You can measure the third dimension, which is into the page, just by optical interference. And for the device, the actual device we're going to use. And this is a TE mode, and this is polarized like this. There are also TE modes like that. They both have band gaps like this and like this. And what we want to do is push the cesium D1 transition at 894 nanometers here, and D2 at 852 here. And this calculation is take that SEM image, digitize it, put it into a FDTD solver, and calculate the image. This is not from the AutoCAD which we started with. This is for that piece of diagram. And you get that. And so now what we want to do is take the cesium transition here, and in this cartoon, move the cesium transition from dispersion regime to reactor regime, outside the reactor. We can't do that, so what we actually do is harder to do in PowerPoint is move the band structure by heat. So that's what we want to do. But how do we know that any of this is, that's a pretty picture, and then we got that. How do we know that this device really respects the span structure? Never mind atoms. So what we do is send light in and get reflection, send light through and get transmission. And the reflection and transmission is a function of frequency. This happens to be transmission. The black is what we measure. And the red is a model that takes into account the SEM photo. And the correspondence is pretty good. That's important because these peaks are just little cavities. You have an impedance matching segment, adiabatic taper. It's not perfect, so light comes down and reflects. Reflection coefficient is about 45%. It's not much of a cavity, but these peaks come from light inside of it. So that's good. And from that fit, you can then actually see from these data, here's frequency and here's the group index and group. And what we're going to do, the experiment I'm going to show you is near the bandwidth and has a group index about 10. So that factor I showed you of enhancing due to the slow light inside the structure about 10 times. And the blue is how big is the reflection coefficient of the below the so not much for, my life was spent with cavity 3D where the reflection coefficients were 997, 999. So we got to trap some atoms near this structure, and those atoms are going to understand if they're outside the band gap, they're going to see this structure. This is detuning, and if you send light in, what is the light intensity is a function of distance along and then we're going to go into the band gap with the atomic frequency. So in the band gap, there shouldn't be any light, but you can see this tails off a little This is a theoretical calculation, and this is what we actually measure. So this is this first resonance. This is the second resonance. It has no halfway difference. The first resonance was right here, the second resonance, and so on. That's a length scale. We know the frequency we put in, so now we know the frequency and length scale, and we can reconstruct the data. And the dots are our measurements from those kind of images. And this is that picture I showed you, the band diagram calculated from this. And I would say that this is a miracle. That we've worked for several years to understand how to build this. And this says that what we have in there really knows about the field of the photon. Doesn't just look like a photon. So with that, we can do an experiment. We can put the atomic frequency there and then tune into the band and see what happens. So the way we trap the atoms is by a reflection trap. We reflect off the surface, light comes in, reflects back. As it reflects back, there's not a very big reflection that you get standing there. The light up here reflects back, and we're trapping out in there. And if you zoom in, these lines are wiggly because all of this has to be calculated with every point that this has an over potential. And that's where we want to trap the atom. The edge of death for the atoms is this to the corner. That's the shallowest part of the holder. And this is what mode looks like along there. And we send light in and out, and we can measure stuff. So the first thing we can do is we measure spectra, and I'll show you in a minute. But the other thing we do is when the atoms are trapped, it's called atom physics, and there's some procedure to get the atoms trapped near the surface. And now you see, as a function of mean number of atoms trapped, you see the decay rate. And the decay rate, by two different techniques of loading, is some total decay rate plus this emission equilibrium. And here, as the number goes to 0, when we trap no atoms and we try to excite them, we get no fluorescence. There's just no background. And so when an atom is there, we don't really know to load one atom. We're not able to achieve that yet. But when there is an atom there, and only one, because mostly there's 0, we get some decay rate which is just gamma 1 equals gamma 1. And that's this total rate. And then when you put more atoms there, the rate goes up nearly the super radiant. And that's just because of the way the block mode is, we have the band range. Every atom's in phase with each other, goes up like that. And from that you can extract that the super radiant decay rate is about 1.1 times the rate. So this is Chindle and Hung's green function calculation zoomed in again. And what we're going to look at is at the frequency we're working, everything is aligned here, about part 2 to the 5th. The band edge of the structure to this. What you see is the gamma 1D is about 1.1, gamma 0, that's what Chindle said we should do. The gamma prime is about the same size for one atom. If we put 2 atoms in, then this atom can emit and induce that guy to emit. That's a super radiant. How big is that? That's a imaginary part of some 2-point Green's function. This would be the dots or the numerical calculation. And what we measure is that this should be 2.1, 2.2. We measure it's about 2.3. And that's the most important thing we've done in all these years, is to validate we know where the atom is. We know the character of the Green's functions that cause the atom to be interactions between atoms. And so this is not just light scattering all the way down there. Here they have what's going on. There's an atom right. Okay, so let's now go. That's in at this first resonance, which has this real and imaginary component. Let's now tune the atomic frequency in the band gap. When we do that, we'll have both cooperative dissipation and this cooperative reversible. And the ratio of those two, this graph is just to show you go in the band gap, that ratio rises exponentially. That's the second explanation I've told you about. I don't think that exists in optical physics anywhere else. that the dissipated part of the interaction is reduced exponentially. Okay, so here's what line shapes look like. We can analyze those line shapes with some kind of formalism that's been looked at by Anselmo Hood and Derek Chang's. And I won't say much about that, except to say, look, they're atoms, and these are Heisenberg operators, and they're evolving. How does this atom know about another atom? This thing, these symbols, are just the two-point range function. An atom's here, and an atom's there. An atom radiates, and how does it talk to another? There's an imaginary and a real component of it, and that's how they talk to each other. And so, at some level, we're beginning to validate this. If you do lots of spectral measurements, you can pull out the dissipated part, the collective decay, and super radiance. When you go into the band gap as close as you can tell this decays. Cooperative level shift is just this dipole-dipole. Some people call it different versions of Lamb shift. And what you see is when you go inside the band gap, the dissipated part of the range function goes to zero, and the real part is dipole-dipole interaction. So this is, at some level, the point of all this effort. It's just the fitting function that we showed you, that just showed you first, compared to what this would look like if that first resonance really were a cavity resonance of the detune. In that case, you still get an increase as you detune from resonance. But since you're revealing the natural components, this is something a little scaled differently in detune, and that's this curve. But this curve actually rises exponentially faster than this curve. And I think that's the first time that it's been demonstrated in this curve. And that was the whole point of this golden experiment. Okay, so quickly let me tell you about what we're doing. This is a new kind of one-dimensional photonic crystal. The light's going to propagate through here. You have to get from the outside world into this, so there's some gigantic impedance mismatch. That's why there's this goofy looking crocodile. So light goes this impedance message efficiently, and then that's the photonic crystal. What is it? It's a slot wave time. This is vacuum, and then there's like a 2D photonic crystal on the outside. And I'll tell you why that's there. And the goal is to trap atoms inside of it. And if we could do that, then this ratio again, 1 to the prime would be 30. But this photonic crystal is not arbitrarily drilled. It's drilled so that when the atoms are radiating in here and they look laterally, they see a band of the two-dimensional photonic crystal, and they can't radiate. So we are able only to show in calculations, not the measurements of atoms, that that rate goes from 1.1 in the alligator, just shows you that drops down to 0.65 in the with quantum dots, people have shown a factor of hundreds of percent. So the two things, by engineering the band structure of this thing, much more flexibility than flattening, this can go up towards 100, and this can go down to 100. At this level, though, this is stuff we measure, that means that one atom has optical depth of 10 minutes later. We measured other stuff in the background. How do we do in terms of material quality? All of this is at the dielectrics, not really low loss. Time. In the short story, this is a photonic crystal mirror. This is a cavity with a mirror. This is gleam, and by using these cavities, we can very accurately assess the losses of various structures. And we've been able to demonstrate quality factors. We're making 2D things. This is a square lattice, a various lattice constant. This is this hexagonal lattice that I'm really interested in itself. If you remember this hallway problem, topological properties, where we multiply lattices, projected band diagram, measured band diagram through all of it. We learned how to get light from waveguides into this complicated structure. We go from this to the structure. And then a question that's the grand challenge. There's all this physics. This right now is a field that's just dominated by theoretical stuff. There's not enough measurements. So the grand challenge right now is to make this happen. How do we take atoms from somewhere and fill this thing up the way it should? You know, nobody knows how to do it. Should we drop them from above? Should we bring them from below? It's the big challenge, and nobody's close to knowing how to do it. So one thing we're doing in my lab, which I'll show you more about tomorrow, is you take an optical lattice, it's just moving along, two lasers, you make a lattice, and you change frequency along the lattice sweep, and sweep these atoms through the photon crystal. No atoms trapped in it. And boom, there they are. And then this is more realistic. That's the alligator. These are trapping sites. This conveyor belt of atoms comes through every now and then, manually we succeed in trapping them. And the tracking technique we're using, I'd be happy to talk to you about. There was something Mark Raising came up with, where we don't have any time. These are so small that even atoms that are at 100 microkelvin move through this thing in a microsecond. We just don't have any time to cool. So we're going to use a technique that Mark pioneered, where you can transfer atoms from one potential to surface to another, one photon at a time. And the projections are we have a micron, a millisecond of atoms running through, and so this lattice moves through in a millisecond, and we only have 200 atoms. The photon crystal only has 150 lattice sites, so a millisecond. So that's what we're looking at. So this is a cartoon that Alejandro drew. This is this 2D structure, this little photon cloud. So the John in 2 dimensions, these things are talking to each other. I really don't, it's my whole life trying to get atoms, photons to interact. And now it's like, why did I waste my time with all that other stuff? This is what I should be doing. If you want to read more about it, we have a review on physics that it took forever to finish, but it's now accepted.
Questions?
So I have a question on the many-body interactions. So once you fix the structure of the Nanoscopic system, then it seems the Commute function is fixed, so the interaction between the any two sides is fixed. So what's your vision of engineering the interaction between atoms?
I went through that pretty quickly. And I'll talk a little bit more about it tomorrow. But if you just take a structure, and let's just do a 1D structure, then if you tell me how far away from the band edge you are, say in the metal, then you know the skin depth, and then you know the attenuation. So we can change that exponential attenuation by changing the tuning between the band edge and the atom, and we know how to do it. But that's kind of restrictive. So what we have, I just flashed it up for a minute, is a protocol whereby if you tell me the Hamiltonian you want, build a structure, and if you tell me the Hamiltonian you want, where it's how big is the XX and Y line is Z, and what it should look like as a function of space. We know how to engineer that by using auxiliary lasers and frequency field. Imagine that you have the alligator, for example, and you put a magnetic field gradient. Then every site has a different hyperfine splitting. So if I want to talk to that site and this site, I use a laser that draws the long-line transition for this site to make a photon, and a different frequency to drive the laser that makes the long-line transition a little bit shorter. And we've counted up all the resources and done a really serious calculation in the DNAS article I put up there. This is a technique that's pioneered in optical lattices, and it really should, regular free space lattices, it all really works to give us arbitrarily to the time reversal violated with arbitrary coupling. If you just want the I minus J to be 5, that's it. Translation invariant. We know how to do that. And we know how to wire the ends together. So it's like so I gave that example of Haldane Shastra. You can't do that without this ability to engineer the IJ between arbitrary sites.
excuse me. So, in the this exponential enhancement that you get in the relative strengths of the coherent versus decoherent interaction, is I guess it's the superradiance or subradiance that's giving that. Is that correct?
There are two. I'm confused a little bit about your question. There's this thing that Anna did where you can store with exponential
Right, that's the thing.
infidelity. So are you talking about?
Yeah.
So
That's not the same physical effect that you were talking about.
no, there are two exponentials.
Okay.
One is that if you have a bunch of atoms and their space less than lambda over 2,
Right.
they're not able to radiate into free space.
Okay.
They're all subradiating. And if that's an infinite chain, then the atoms, this spontaneous emission of free space is strictly 0.
Mhm.
So if you make a finite chain, all the losses have to do with the ends. If you take a finite chain and put it back on itself, there's an exponential suppression. So in that case, the honest trick was that it's just the end loss. So say in an EIT mapping, tailor the control field so that the ends taper away slowly. And that's what gives rise to exponential method. In the case of essentially the real and imaginary components of the Green's function, it's that in an infinite photonic crystal, the Green's function only has a real part. It's only spin exchange with whatever length state. And the real part, the collective dissipation is 0. So in finite photonic crystal, there's some length associated with this atom seeing the ends because it's only exponentially suppressed. But it is exponentially suppressed associated with the size of the crystal compared to the size of the sun.
Yes, I guess that was my question. What ultimately, what do you have to control to get to this exponential volume? I mean, what?
Well, the cheat in that story. Don't say that.
I think
turn the camera on. Is what I said is all true, but what's left out? The atoms are in a waveguide. They can have collective dissipation, that's exponentially suppressed. They can have collective spin-spin interactions, that's just fine and dandy. They also radiate to free space. So we have to control this gamma prime. So the solution to that is this engineering of these slot waveguides and the engineering of the structure to suppress the free space emission. So if we did as well as Peter Loden's demonstrated, we could get 100-fold of gamma prime. We can always detune from resonance and get around the delta spin and have these other things still be exponential. But finally, that gamma prime comes into bite us. If I want to even minus a twin, it's big enough. We really have to control the gamma prime. But there is a community knows how to do that. So U has been building little structures in 2D and putting atoms in them. He gives 20, 30 degree suppression. But how do you do that in the lab for real? So that's But at the level of one atom, at the level of one excitation, honestly, already works. If we can trap atoms like that, their spacing is subregional. And all these theories, including ones that I've done in this paper, are wrong. Because the spacing, gamma prime is no longer a single atom event, and all these papers have called it that. And so then we get for free, if not exponential 100-fold, we get a 1 over n² suppression. So we've got to drive gamma prime down. The honest thing, the particular thing is for one photon mapped in and out. If you want to do 2 photon stuff, then you lose by a factor of instead of 1 over n², it's m over n², where m is the number of excitations. So I think there are the tools there with Anna and Derek to really use them in optical fields.
You might have missed it, but with the guide, how is it that you create lattice sites? Is it because of the periodic index for refraction outside of the guide? Is that how you create those lattice sites where the atoms are trapped in the top of the lattice?
Are you talking about the experiment or the?
Yeah, the experiment, like the
So
actual
in the experiment,
trapping.
if you just take a plane wave and reflect from the dielectric, then the light comes in, reflects, pi out of phase, and so when you move a distance lambda over 4 from the surface, you'll get constructive interference. The light that's coming in and the light that came back are phased to add up. And so you get in a perfect dielectric, you get reflection and phase change. And so then you go away, and then you get an enhancement, and that makes a bump.
Okay.
That makes a
happens
bright
along
spot.
the
Makes a
long
bright
axis?
spot. So if you go like this, then in just a plane wave, then you would get bumps at lambda over 4 from the surface. You get trapping sites. You get intensity maximum.
Okay.
And now when you do that off of this guy, the story transversely is the same. It doesn't matter if it's 30 microns strong. But if you do it along the device, it reflects, and then the trap is this very shallow, doesn't know about. Surprisingly, the reflection from the photonic crystal like that, the interference, the field that comes off, has very small modulation of only a few percent, even though there are these teeth that are doing the reflection. But that's where it came from. The first group to demonstrate the experimental was Michel Lucas and Glenn Gould, Jeff Thompson, was interested in Korean experiments reflecting off, in his case, a tiny little photonic crystal cavity. And then the advantage of that is the trapping site is aligned exactly. You know, you send in a laser and you go like that, and it doesn't matter if it's 30 microns, something like that. The thing that makes the bright spot is the dielectric structure itself.
How cold do the atoms have to be to load them into that?
And we start with 10 or 20 microcoulomb. The trap depths range from 800 microcoulomb, but where the atoms can get out is maybe 3 or 4 times colder because of the plasma colder stuff. So 150 or 200 microcoulomb they escape. In some of our experiments, the trap's running 300 microcoulomb deep, and then the escape via plasma colder is 50 microcoulomb. The measurements I showed you was 50 microcoulomb. So the atom temperature, that sets the limit. And you could do what the lifetime would be versus the lifetime. And we infer 20 microcoulomb or something.
We're looking forward to listening to your fluid tomorrow. So let's thank the speaker again.